Welcome students to Darasa Online. We have another chemistry session. Our same topic that we did last time. We are still in formula, bonding, and nomenclature. Now remember last time we talked about valence and chemical formulas. We also talked about some effects to do with writing of chemical equations. But today, let's try to have this session to talk about something that to do with radicals. Remember last time we were talking about the chemical formulas. We talked about binary compounds. We did not mention anything to do with radicals. Today, after the mention of radicals and after discussing together, I do believe we can now be able to incorporate the radicals in our chemical formulas. Welcome, your teacher is Kenneth Kaunda. Now, let's talk about radicals. Now, students, if you remember the last time we were discussing together the issue of formulas, chemical formulas, we mentioned the use of valencies in trying to obtain chemical formulas or using the symbols to represent the compounds that we normally have when we bring two atoms together. Now, if you have not forgotten the trend or how to get the valencies or how to get the formulas of binary compounds, now let's try to remember those aspects of the concept that we learned so that we can be able to get the same radicals now and then incorporate them into our chemical formulas. Now let's try to remind ourselves, before I introduce the topic of radicals, let's try to remind ourselves about the valencies and chemical formulas of the binary compounds so that we can be able to use the same idea in trying to write the formulas for radicals. Now we said for a binary compound, let's say for example, a binary compound is a compound that is consisting of two elements combined together using chemical symbols. So if you have a compound, for example, sodium and chlorine, and then you combine them together, you can get a formula of sodium chloride, then we said you have to check on their valencies, interchange the valencies, and get the correct formula. So we said if valency of sodium is 1 and also chlorine is 1, we exchange them. Then because the same value, it is sodium chloride. So the formula of sodium chloride using the binary compound is NaCl. Now if you have something like calcium and then you have something like chlorine, then calcium is 2, valency of 2, and also chlorine valency of 1. Now we said after writing the valencies and the symbols, we interchange the valencies. So if I interchange 2 to come here and 1 to come here, then our formula is calcium 1, which you don't write 1, then write Cl2. This is a binary compound. Now today, we want to check not on binary compounds, but we want to check the reactions or the formula of compounds formed between, let's say, metals and radicals. Now a radical is something like a carbonate. Now a carbonate is a compound. Now here we are talking about an element combining with an element. But now in radicals, we want to talk about an element combining with a radical. Now that one brings us to the concept of radicals. So let's try to check what are radicals. Now, a radical is a group of atoms, just like I wrote here CO3 minus. I would like to use this example to explain what is a radical. This is negatively charged. Let me write what is positively charged. Let's talk about ammonium ion. Let's talk about these two. So a radical, as you can see, it consists of not only one element, because if it were one element, we're talking about a binary component. There are two elements here, carbon and oxygen. There are two atoms here, nitrogen and hydrogen. So it means a radical is a compound consisting of not one atom, but a mixture of a number of atoms. There can even be 3 atoms. These are 2. For example, if you have got something like hydrogen carbonate, it consists of hydrogen, carbon, at the same time oxygen. Then it forms one complete unit called a radical. Now a radical behaves or reacts just like a normal element. So if we say sodium combines with a carbonate, then this carbonate will behave just like the original chlorine we are using in sodium chloride. So a radical will behave exactly as a single atom in forming in chemical reactions. So let's have our definition. A radical is a group of atoms. A group of atoms that behaves or exists as a single atom, e.g. in chemical reactions or in writing their formulas. A group of atoms which behave as one single atom. So here a carbonate is a group of atoms because it's a group of carbon and oxygen, but it behaves as a single atom. So when we react sodium and a carbonate, it's just like the same as saying sodium plus another atom X. So we'll have sodium X. So where X is our radical. Initially, in our last sessions, we said X is a particular element. So sodium reacts with an element X to give us sodium X. Sodium reacts with a radical to give us sodium plus the radical. So this radical behaves as a single atom. Now, from the examples that I listed above, I listed an example of a carbonate and also an example of ammonium ion. So if we look at a carbonate and also ammonium ion, then we realize something about radicals, that all radicals are charged. Remember, we talked about oxygen states in our last session, and we said oxygen states are always monitored by the charges that we put on their formulas. Now, all these radicals are charged, and we must show the charge of the radicals upon their formulas. The question is, are these charges useful when you're dealing with radicals? Now, the charges act as oxygen states of the radicals. Now, remember when we said when writing chemical formulas, we said for us to write a chemical formula, we must know the oxygen state of a particular species. So if you know an oxygen state of a particular species, then automatically you can be able to combine a number of them to give us a good formula. Let's say, for example, you want to combine, let's say, magnesium and a carbonate. Now, this carbonate shows that the species has acquired 2 electrons because of the 2 negative acquired electrons, because the radical looks like it is highly electronegative. Now, these 2 electrons came from where? They came from magnesium. So you can say if magnesium is have an oxygen state of 2+, and then a carbonate has got an oxygen state of 2-, then we exchange this as usual. Then we have our magnesium carbonate to be MgCO3. Remember, we said you exchange. So we'll have our 2 there and our 2 there. And we said if they're the same, then they'll cancel out. So it'll just become magnesium carbonate. So in which case we have used the 2 negative there as the oxygen state of a carbonate or the radical. And you know the state of magnesium is 2 positive. So the negative sign or the charges that we have on the radicals gives us a very good way of writing the formulas of the respective compounds. So we say all radicals are charged, and the charges are not for the specific atom in the radical, but for all the atoms making the radical. At the same time, we say the charges the values of the charges are typical of their oxidation states. Something like S04, 2 minus, has got an oxidation state of -2. So when you're writing the formulas of compounds of radicals, then we use these charges as their oxidation states. That one can give us a very direct way of writing different formulas. Well, let's try to look at examples of radicals that are very commonly used and that we can be able to know. There are so many radicals that you can be able to mention, but you can just mention but a few. Remember, when you write a radical, you must write its charge. We have the one we have just talked about, which is ammonium radical. We have SO4, 2 minus, which is a sulfate. We have SO3, 2 minus, which is a sulfite. Here we have got the valency of 1. Here we have got a valency of 2. And here also a valency of 2. Also we have HSO4 minus is called hydrogen sulfate. A valency of 1. We have got also HSO3 minus from the HSO3. This is hydrogen sulfide. We also have CO3 2 minus, which is a carbonate. We have HCO3 from the same carbonate will give us a hydrogen carbonate. We also have Cr2O7. This is called dichromate. But Cr04 is called chromate. We have S2O3, 2 minus, this is called thiosulfate. We can say, etc. There are so many of them, students, which you can be able to write. Because we are doing revision, and I'm tempted to believe that all these have been taught, then we just jog our memories and come up with a good number of them. You can write as many as possible so that you can be able to remember them all the time. Because these things, you need them in the exam. Now, in the exam, when you are there and then you forget about a particular radical, especially if you forget about the charges, then you cannot be able to write a good formula of those radicals. Now, once you have known the radicals and their charges, especially the oxidation states or the valencies, then you can use that information to write formulas of compounds which consist of radicals. Now, formulas of compounds comprising of radicals. As I said initially, that we looked at the formulas of compounds which were not containing radicals, just binary compounds. Now, because we skipped this kind of stuffs, now today let's try to incorporate these radicals into our formulas of compounds. Then you can be able to complete this subtopic of formulas. Now, before we go to the direct formulas, I would like to mention something about the metals, just as a reminder. In metals, we said there are some metals that have got what is called variable oxidation states. So in our last class that we had, we discussed about oxidation states, and we mentioned something about the variability of some oxidation states. That means there are some metals which lose as many electrons as possible depending on what they are reacting with. For example, if I talk about something like iron, iron has a valency of 2. But iron also can have a valency of 3. It simply means that if iron is reacting with a particular species, then it can opt to give out 2 electrons. At the same time, it can also opt to give 3 electrons that species. Now, if it can give 2 or 3, then we say it has got what's called variable valency or variable oxidation state. It means that it has got so many electrons in its shells such that it can decide to give 2 or 3 depending on the requirement of the species it is reacting with. For example, in our discussion on rusting, for those who are present during that discussion, we wrote a formula about iron oxide. Now, our iron oxide there was iron 3 oxide, but we can also have iron 2. It means that if iron reacts with oxygen, we can get iron 2 oxide, but at the same time, iron can react with oxygen to give us iron 3 oxide. Now, if this is the case, we cannot write the formula of iron oxide, because if you write iron oxide, somebody will not know which oxide are we talking about. Are we talking about iron 2 or iron 3? So those metals that have got variable oxidation states in their formulas, we must specify the oxidation state of that particular metal. And remember, we discussed when writing formulas that the oxidation states must be placed in brackets after the name of the metals. For example, this one is supposed to be called iron 2 oxide. Why are we saying it's iron 2 oxide? Because we have got an iron which has a state of 2 combined with oxygen which has a state of 2, negative. If we interchange these valencies or the states, then we'll have Fe2O2. And from our discussions, they are the same. If they're the same, we cancel them. So it becomes FeO. And that's how we have FeO. Now, if you just write FeO without telling us it is iron 2, sometimes you can assume and you can make a mistake in terms of naming of a particular component. So they must mention if they are variable. So a good number of metals have got that kind of species. So the metals having variable oxidation states can opt to react by giving out electrons depending on the extent of oxidation and also requirement of the species they are reacting with, or they are combining with. I've written the word oxidation. In our last session, we talked about oxidation, and we said oxidation is loss of electrons. Because this metal is losing electrons, it's undergoing oxidation reaction, loss of electrons. Now, losing electrons depends on the species, requires how many electrons. At the same time, iron is also looking for stability. So looking for stability and the requirement of the particular electron element which is reacting with can give us an idea of the kind of oxidation states. So we say when writing the name of such compounds or compounds of such metals, the ones having variable oxidation states, then the oxidation state of the metal has to be written or given in Roman numerals in a bracket after the name of the metal. E.g., we can have this one here. O is ion 2 oxide, in which case this 2 here is the oxidation state of this ion in this situation. But this one here, 2O3, is different from this one because this ion is not the same as this ion. This is ion 2 and this one is ion 3. So you have this is ion 3 oxide. So because ion has variable oxidation states, our statement says when writing the names of the compounds of such metals, then the oxidation state of the metal has to be written in a bracket. So this has to be written if a particular metal has got variable oxidation states. There are not very many metals, but transition metals have got this kind of habit of variability in their states. So we say other metals with variable oxidation states are copper. We can have copper, where we can have copper 1 and copper 2. We also have got lead 2 and lead 4. At the same time, you also have manganese 2 and manganese 4, etc. Now, these metals which have variable oxidation states, you're supposed to master them because they are not very many. And if you have experience and use them all the time, then you can be able to remember them all the time. Because at the end of the day, in most of your exams, you'll find these metals writing their compounds and calculating their oxidation states. So let's look at a few examples on how to write the formulas of compounds where radicals are used in the formulas. Write the formula of the following compounds. Let's have number 1. Let's say it is sodium carbonate. Sodium carbonate. So sodium is just a metal. We're supposed to know its oxidation state or valency, which is 1. Carbonate is a radical in this case. We've seen a carbonate has got an oxidation state of 2 negative. So when writing the formula of sodium carbonate, then we are supposed to specify the valencies or the oxidation states, and then we exchange as we learned before. So we have sodium as a valency of 1, and then we have got our carbonate as a valency of 2. Then if you exchange these, then we'll have sodium as 2, and then carbonate as 1. We don't write the 1. So this becomes our formula. The second one, we have something like aluminium, let's say aluminum sulfate. Aluminum sulfate. So our metal is aluminum and our radical is a sulfate. Remember, our sulfate radical has a valency of 2 because the state is 2 minus. Aluminum is in group 3. We said the valency of group 3 is 3. So we have aluminum as 3, and then we have got our sulfate as 2. Then if you exchange these, then we have aluminum 2 and then a sulfate. There are now 3 of them. Now that one becomes our aluminum sulfate. How about a third example? Ammonium carbonate. Ammonium is a radical and a carbonate is also a radical. But two radicals can combine together because ammonium radical is positively charged and then our carbonate radical is negatively charged. So because negative and positive, still they can also come together. So we have ammonium, which is positive 1, and then you have our carbonate, which is negative 2. And as usual, if we exchange the values of the valencies, then we'll have ammonium with a 2 now, and then carbonate with a 1. And now that one becomes our ammonium carbonate. Let's look at another example. Number 4, let's have magnesium, hydrogen, sulfide. I'm saying magnesium hydrogen sulfide, and I don't mean a sulfate, it's a sulfide. Students normally confuse a sulfide and a sulfate. So if I write a sulfate, these two things are different. This is SO4, this is SO3. Many students confuse those two terms. So magnesium is a metal, but the hydrogen sulfide, this hydrogen sulfide is not a metal or non-metal, it is a radical. So if you know its formula and its valency, then you can combine it with magnesium. This one is HSO3 minus, and this one is Mg2 plus. So if we are to exchange, we can write 2 plus to minus, or you can write 2 and 1. Because we have been used to writing the valencies, let's try to go with the same method. So this one has a valency of 2, this one has a valency of 1. Remember we said the oxygen states have got charges. The value of the charges are exactly the same as the valencies of the radicals. So we can exchange our 1 to come there and 2 to come there. So we'll have magnesium, hydrogen, sulfide. Now magnesium is 2, this is 1, so our 2 comes there. In some situations, we are learning the radicals. Some situations, we are given some names which does not exactly rhyme with what we have. For example, if somebody asks you to write the formula of something like lithium bicarbonate, let's use that just as an example. It might not exist, but let's try to use, because what my interest is, what is a bicarbonate? A bicarbonate is a hydrogen carbonate. So next time you see a bicarbonate, because you have common ones like sodium bicarbonate, it is only hydrogen carbonate, which is a radical. So we have our lithium, which is a valence of 1, group 1. Then we have got our hydrogen carbonate, which is also having a valence of 1. If you exchange the 1 and the 1, we don't have any difference. So our formula becomes LiHCO3, and already we have our lithium hydrogen carbonate or lithium bicarbonate. So bicarbonate means hydrogen carbonate. We can also have another example. Let's say we talk about something like ammonium, which is our only positive radical. Ammonium dichromate. Our radical is dichromate, another radical is ammonium. So we are supposed to know what is the real formula of a dichromate. A dichromate is Cr2O7, which is negatively charged. Then ammonium is positively charged, NH4+. So if you are to write the formulas, then we expect to have ammonium, which is 1, and then Cr2O7, which is 2. And then we exchange these values. Then you have our ammonium, which are now 2 molecules, and then we have got our Cr2O7. Now that one becomes ammonium dichromate. Now students, until this 6th example, we've been trying to write formulas when we are given the names. What if you're given the formulas, now we want the names? Let's say we write the names of the following compounds. Let's say number 1 is Fe2O3. And then let me have the second one as PbCl2. This PbCl2 and Fe2O3, the first thing that should come to your mind, ask yourself, are the metals having variable oxidation state, or they have a normal oxidation state? So you're supposed to identify before you start thinking of how to write the formula. I know iron has got variable oxidation state, so I have to be very careful when I'm writing the name. I have iron, which is 3, and O, which is 2, because these things exchanged before they came here. So if this is the case, then I know the state of iron is 3, so I have to write the 3 upon the name. So this will become iron 3 oxide. The 3 means the state of iron. So try to go back from where you are and then try to get the correct valency. In this PbCl2, I also know lead also has got variable oxidation state. You can have lead 2 or lead 4. The question is, what's the valency of lead here? So I have to go back from the answer. Pb is 2 and Cl is 1. If I exchange, then I'll go back there. It means this is lead 2 chloride. Based on this kind of scenario, if you're given a number of formulas, then you're supposed to write their names, then the first thing you should do is to try to see if the metal has a variable oxidation state. It's very different from if you're given a formula like something like KCO3. Now, KCO3, we know this is potassium, but potassium does not have any variable oxidation state, so it simply becomes potassium carbonate because we don't have to add the valency of potassium in between the formulas because it does not have a variable oxidation state. Example 3, let's say we have got magnesium phosphate, magnesium PO4, 3 and 2. Magnesium does not have a variable state, so the name just appears as it is. This is supposed to be magnesium phosphate. If you have the fourth one as Al, HCO3, 3. Then we'll have aluminium, hydrogen, carbonate. What if you have something like K2, Cr2O7? This is a dichromate, and this is potassium. Potassium does not have a variable oxidation state, so we'll simply have potassium dichromate, and that one gives us the formulas. Remember, when given a formula, then you're supposed to write the names. Please try your level best to check whether that metal has got variable oxidation state so that make mistakes. Many students make the same mistake because they don't know how to identify between metals without the variables and the metals with variable oxidation state. Now, students, will take a short break. When I come back, we'll be having some questions that we are supposed to handle. After handling those questions, I do believe that during your study on the exams that you're going to do, you'll not have any problems in this kind of subtopic. Thank you. Welcome, students, to Darasa Online. We had a session, we were discussing about radicals in our topic of formula, bonding, and nomenclature. We discussed a number of issues, especially the concept of radicals. We explained what radicals are, a group of atoms that behave as a single atom during chemical reactions. We also talked about their structures, how they are. You see they are charged, and the charges are just like the valencies, and also say that the valencies of these radicals does not belong to a particular atom in that radical, but belongs to the whole radical itself. After that, we also discussed about writing formulas, and when writing formulas, we put a lot of emphasis, especially on the metals that have got variable oxidation states, because a number of students normally confuse the writing of these formulas. And we said when you are having a metal, especially transition metals like lead, copper, iron, manganese, those ones which normally have variable oxidation states, we said you must specify the oxidation state of that metal when you write the name. That means when you're writing the name, you start with the metal, and then in a bracket, you write its oxidation state, and then you complete with the other components. We looked at some of the examples of writing formulas, and then I do believe from that experience, you can be able to answer some questions that you can also face. Now let's go back and see the questions that we have. We can be able to handle them. There are many questions, but you can see how much you can go. If there's time, we'll complete them. If there's no time, some you'll have as an assignment. But let's try and see how far we can go. Our first question is saying, name the following radicals and state their valencies. Name the following radicals and state their valencies. We have got the first one is SO3 2 minus, the second one is CrO4 2 minus, and S2O3 2 minus. So we have the first one is SO3 2 minus. We have got CrO4 2 minus, and you also have S2O3 2 minus. These ones are radicals because, as you can see, they are charged, and it's not a single atom, it's a group of atoms. So we said a group of atoms which are written in this fashion, they are called radicals. Now, this one has a valency of 2. This one also has got a valency of 2. This one also has a valency of 2. But now, what are their names? We don't have a specific formula to know the names of radicals. We're supposed to get experience in using them and mastering them, so that at the end of the day, in our heads, we can be able to know when you're given a particular component, you know this one is this and this one is this. So this one, SO3, like I said, is different from SO4. So I hope you remember I wrote something between SO4 and SO3, because many students confuse these two things. Whenever they see SO, they think of a sulfate. This one is a sulfate, but this one is a sulfide. So this one here is called a sulfide and not a sulfate. This one is called a chromate, and this one is called a thiosulfate. Thiosulfate. From experience, if you're using these radicals quite a number of times, then these things will always be at your fingertips during your writing of formulas. Our second question is saying, write the formulas of the following compounds. Write the formulas of the following compounds. In this particular question, before you start answering the question, there's a hint. Try to check if there's a transition metal with variable oxidation state. If there's no, then continue normally. We have aluminum phosphate. So here, aluminum is a metal. It does not have any variable oxidation state. We take it as a normal metal. So we have aluminum with a valency of 3, because aluminum has got 3 electrons in the valence shell. Then we have got our phosphate. Our phosphate here is a radical. So if it's a radical, we have to know its charge, which is -3. So we have got PO4 -3, which is 3. So we exchange these ones, then it becomes Al3 PO4 3. And then from our experience, if they're the same, then we cancel them. So this one cancels that one, so that we have AlPO4. Now this one is our aluminum phosphate. The second one is copper 1 sulfate. Students, in this question, we have a bracket here in the middle. Now this bracket shows that the oxidation state of copper is 1. Remember, we said copper has got variable oxidation states, either copper 1 or copper 2. In which case, in our question here today, we have copper 1. So we have our copper, which has got a valency of 1 for this bracket. And then you have got our sulfate, which has got a valency of 2. Now if you exchange the valencies, then we'll have our copper, now 2 there, because the 2 has come there, and then you have got our sulfate. Now this one becomes the formula of copper 1 sulfate. Then you also have part C, we have got iron 3 carbonate. Iron 3 carbonate. Still, just like in copper 1 sulfate, we have got a bracket with a Roman numerical value, which means this is the oxidation state of iron. Our carbonate is a normal radical with a valency of 2. So we can have our formula as iron, a valency of 3. Then we have got our carbonate, a valency of 2. And then we exchange the valencies. Then we have got our iron now is 2. And then our carbonate now is 3. So we have got our iron 3 carbonate. Part D is ammonium hydrogen carbonate, and ammonium hydrogen carbonate we are done in our previous examples, so you can be able to handle that part. Our next question, question 3, is saying, write the names of the following compounds. Now we are given the formulas, then we write the names. In the question number 2, we are given the names and we write the formulas. Now this is vice versa. Let's see what you can be able to do. Part A is saying K2 Cr2O7. What's the name of this component? We know this one is our metal, but we know this one is a radical. So we have got a metal potassium and our radical Cr2O7. From our experience, in even the previous examples we have done, this radical is called dichromate. So if dichromate, then the name will become potassium dichromate. We are not writing anything between potassium dichromate in a bracket because potassium as a metal does not have variable oxidation states. Part B, we have Ca3 PO4 2. again, this is a normal metal, and this one is our radical. So try to identify the metal and the radical, and identify the metal, try to see whether it has variable states. Calcium does not have any variable oxidation state, so we take it as a normal metal with valency of 2. Calcium is 2, and then phosphate is 2. So if we have the formula now, we can be able to get the name. It is calcium without a bracket, and then we have got a phosphate. Calcium phosphate. C, we have CuNO3. Copper is a metal, and then NO3 is a radical, which is a nitrate. But now copper, we have to check, is it copper 1 or copper 2? Now, if you were to write the formula of copper, then you expect copper had a valency here, which is 1, and also nitrate also valency 1. That's the only way you can exchange them. Now, if you do that, then our copper has a valency of 1, or oxidation state of 1. In writing the name, then you must mention that 1 in a bracket. So this one becomes copper 1 nitrate. Copper 1 nitrate. We also have Pb2CO3. That is part E. I've skipped part D because part D we have just done up front. Lead as metal and the carbonate as a radical. Remember lead transition, and it has got variable oxidation state. We said we can have lead 2 or lead 4, etc. Now we have to check what is the valency or the oxidation state of lead in this situation. If we have this formula Pb2CO3, we expect that at this point there's 1, which we normally don't write. So this 1 came from lead, and this 2 came from carbonate. Then they exchanged to get the formula, meaning the valency of lead is 1 and the valency of carbonate is 2. So this one becomes lead 1 carbonate. If you don't do that, then you cannot get the correct answer. Because when you're getting the formula, try to reframe the question in such a way that this valence which are here goes back to their original positions. Then they go to original positions, then you can be able to identify the compound. Part F, we have Na2SO3. This is a normal metal, sodium. This is our radical sulfide. So we have got our sodium, and sodium does not have any other state except 1, and then we have got our sulfide, sodium sulfide. And lastly, G, we have got Al2SO4-3. This is aluminium, normal metal, and a sulfate, so it becomes aluminium sulfate. You can take as many examples as possible. Try to practice on writing the names. You're given a formula, write the full name, or you're given the name, then write the formula forward and backward, then get that experience. The next question, number 4, the question is saying there is no compound as copper oxide. Briefly explain. There is no compound as copper oxide. Briefly explain. Copper oxide. The question asking us why we cannot have something like this. But I can see this is copper plus oxygen giving us copper oxide. So if you say copper plus oxygen should give us copper oxide. It is correct, copper oxide. But which copper are you talking about? Because copper has got a variable oxidation state. So there must be something we must put here as a bracket. Now, what do we put there? We need an oxidation state. So if you simply say copper oxide, somebody cannot know whether this copper oxide is copper 1 or copper 2. So you cannot get something like a copper oxide. So the problem with this name is that it is missing the oxidation state of copper, which must be shown, either copper 2 or copper 1. So you can suppose to have CuO or Cu2O, copper 1, copper 2. Then you can be able to get the correct answer. Question 5 is saying, briefly explain why ammonium ion is the only positively charged radical. All radicals are negatively charged except ammonium ion, which is positively charged. The question is, why is it the only positively charged radical? In this case, we only get ammonium ion when we react ammonia and hydrogen ion. Remember, hydrogen ion comes from hydrogen, which has got only one electron in its valence shell. So if this is our hydrogen, it has got one electron. If it loses that one electron, then it becomes hydrogen ion. Means it does not have any electron at all. So for hydrogen to become stable, then this hydrogen is supposed to acquire 2 electrons to reach what is called a duplet. Remember, students, we talked about stability of atoms. Atoms cannot be stable if they have got stable noble gas configuration structure, where we can have 2 electrons for hydrogen or helium, but you can also have 8 electrons for the other elements. So for hydrogen to be stable, it must have 2 electrons in the shell. So if hydrogen has lost an electron, it means that it is remaining with nothing. So it means for it to be stable, it has to acquire 2 electrons. So nitrogen will have to give it 2 electrons to become stable. So if it gives 2 electrons, then we'll have NH4 positive, meaning we have got 11 protons in this compound, but we have got 10 electrons because an electron has been lost. Now, if you have got 10 electrons and 10 protons, we know protons are positive charged, electrons are negatively charged. If you add this one, there is a net positive charge which is remaining. These are positively charged, negatively charged. So the positive are more than the negative by 1. So that's why we have this positive charge on ammonium ion, the only positive radical in the situation. I also give you a homework. Go to the books that you have. Please try to do as many questions as possible. I'm so happy to have been with you together. Thanks for your cooperation and discussion. I do believe from today you can handle all the questions talking about radicals. Welcome again in our next session.